Hi, this is Imtiaz Rahman. I am presenting my poster titled Impact of Chamber Pressure on Indium Doped Beta Gallium Oxide. I have worked with Pujarani Shaha, Saifal Arifin Toki, Pallab Kumar Sarkar, Jibesh Kanti Shaha, and Dr. Ariful Haq. Now, I'd like to remove my face for the better view of my poster. Now, I'd like to discuss the abstract of our poster. As indium doped beta gallium oxide is very important in bandgap engineering, we worked with 25% indium doped beta gallium oxide. Basically, we kept our substrate temperature constant at 620 degrees Celsius and we vary our oxygen pressure from 1 into 10 to the power minus 3 torr to 5 into 10 to the power minus 2 torr. We found that our sample shows conductivity at high oxygen pressure, while at low oxygen pressure we find our sample non-conductive. From the crystal analysis, we got polycrystallinity at high oxygen pressure, where our sample is close to the single crystallinity at low oxygen pressure. Now, I'd like to discuss the introduction of our poster. Gallium oxide is really important for its ultra-large bandgap, high breakdown field, and high thermal stability. And the current challenges in this field is there are still difficulties on doping, high density of unintended electron carriers, defects or impurities. We use pulse laser deposition to grow our sample. We can tune the substrate temperature, laser repetition rate, growth pressure, and a height between substrate and target to find the optimized properties. We use X-ray diffraction, in short XRD, X-ray photoelectron spectroscopy, in short XPS, ellipsometry, and Hall measurements for our research. Now, I'd like to discuss the experimental setup of our research. We use 2-inch diameter conventional C-plane sapphire as a substrate, and as I have discussed earlier, we have worked with 25% indium doped beta gallium oxide, and we use KRF excimer laser of 248 nanometer, and we use 5000 pulses at a 5 Hz repetition rate, and the laser energy was 250 millijoule, and we kept our target to substrate height 1.5 inch. Figure 1 describes the working principle of pulse laser deposition technique. Now, I'd like to discuss the result and discussions. XRD. Figure 2 describes the working principle of the XRD. From the XRD, we got that our indium gallium oxide thin films exhibits monoclinic peaks at 18.88 degree, 38.16 degree, 58.95 degree, and 81.74 degree. And we also find sapphire substrate peak at 20.51 degree, 41.44 degree, and 64.12 degree. We observed an additional peak at 30.64 degree for high oxygen pressure, which corresponds to the cubic 222 plane. For this, we can call this sample at a high oxygen pressure is polycrystalline. But at low oxygen pressure, this diffraction peak is not that much prominent. So that's why it's close to the single crystalline. XPS data analysis. We analyze the bonding analysis for our sample, and figure 4 depicts the survey spectrum of X-ray photoelectron spectroscopy, in short XPS of indium gallium oxide thin film. If we look at the figure number 5, we can observe that the peak of O1 is located at 529.78 electron volt, which denotes the metal oxide lattices. And the metal hydroxide or carbon-oxygen bond for surface contamination is represented by the peak at 531.9 electron volt. Basically, we can easily say that from the figure 5, the intensity of metal oxide signal is much higher at high oxygen pressure, and metal oxygen lattices can help to reduce drop size, which can lead to a large concentration of free electrons. This may occur at the high growth pressure because more oxygen is introduced into the chamber and the mean free path of the ablated plumes in the chamber becomes shorter, which causes more intense interaction. Figure 6. We also derive the express spectra of gallium 2p and indium 3d spectrum. And we found that at high oxygen pressure of 5 × 10⁻² torr, the intensity of binding energy is slightly shifted for gallium 2p and indium 3d spectrum. And moreover, we assume that maybe there are oxygen vacancy, as we find a peak of O1s at 531.9 electron volt, and oxygen vacancy operate as shallow donors and generate free electrons, which may cause conductivity. Hall measurements. We measured our electrical properties by biorad Hall system. We find our conductive sample as resistivity of 0.05118 ohm per centimeter, and we find a carrier concentration of 1.737 × 10⁻19, and we find an excellent mobility of 7.02. We also measured the thickness by ellipsometry, as we can clearly see that at a high oxygen pressure of 5 × 10⁻² torr, we find the thickness of 250 nanometer, and at low oxygen pressure of 1 × 10⁻³ torr, we find the thickness of 210 nanometer. Conclusion. So 25% indium gallium oxide with a high pressure exhibits good conductivity, where at low oxygen pressure it exhibits poor carrier mobility. Comparative surface analysis of these two samples were performed to investigate this phenomenon. So further studies on structural properties correlation of indium gallium oxide thin films maybe enable us to fabricate efficient next generation HEMT devices. Here are the references we used for our research, and we would like to thank Shared Research Operation of Texas State University, San Marcos, USA. Now, I would like to discuss why our research is really important. We achieved an excellent electrical properties, including mobility, which is the prerequisite to fabricate any practical devices. So we firmly believe that this research will help to produce practical devices with a high performance, such as high power electronics, deep UV photonic devices, and nuclear detectors. That's it. Thank you, everyone.